In this introductory lesson, we will examine exponents and some properties of exponents. Let's begin with some definitions. In this expression, the bottom number here is called the base, and the top number is called the exponent. Now, this particular expression can be read as 2 to the power of 5 or 2 to the 5th power. The exponent 5 in this expression tells us to take the base of 2 and multiply it by itself 5 times. This equals 32, so 2 to the power of 5 equals 32. Similarly, the exponent 3 in this expression tells us to take the base of -4 and multiply it by itself 3 times. So -4 to the power of 3 is equal to -64. Finally, the exponent in this expression directs us to take the base of 2/3 and multiply it by itself 4 times. This equals 16 over 81, so 2/3 to the power of 4 is equal to 16 over 81. Now, as you might guess, we can take products such as this one and rewrite them using exponential notation. For example, this product of 5/8 can be rewritten as 8 to the power of 5. Similarly, 13 times 13 times 13 can be rewritten as 13 to the power of 3. -4 times -4 can be rewritten as -4 to the power of 2, and this product of 7x's can be rewritten as x to the power of 7. Now, please note that expressions where the exponents are 2 or 3 can be read a little differently. For example, we can read this expression as 7 to the power of 2, or 7 to the 2nd power, or 7 squared. So, if the exponent is 2, we can say that the base is squared. In this example, 7 squared is equal to 49. There is also special terminology when the exponent is equal to 3. We can read this expression as 6 to the power of 3, or 6 to the 3rd power, or 6 cubed. So if the exponent is 3, we can say that the base is cubed. In this example, 6 cubed is equal to 216. Okay, now let's examine some special properties related to exponents. The first property concerns expressions where the base is equal to 1. In this example, 1 to the power of 6 equals the product of 6 ones, which equals 1. In general, we can say that 1 raised to any power will always equal 1. So all of these expressions will evaluate to be 1. The next property concerns expressions where the base is equal to 0. In this example, 0 to the power of 5 is equal to the product of 5 zeros, which equals 0. In general, we can say that 0 raised to any non-zero power will equal 0. So all of these expressions will evaluate to be 0. Now, you may have noticed an unusual condition in this last property. For the property to hold, the exponent must not be equal to 0. So what happens if we raise 0 to the power of 0? Well, believe it or not, there is no agreement among mathematicians regarding the value of 0 to the power of 0. Given this, you can rest assured that you will never be tested on the value of 0 to the power of 0. The next property concerns expressions where the exponent is equal to 0. Now, at this point, our current definition of exponent falls apart. What does it mean to take the base of 7 here and multiply it by itself 0 times? It seems that 7 multiplied by itself 0 times should equal 0, but it turns out that it actually equals 1. In fact, if we take any non-zero number and raise it to the power of 0, the result will always be 1. Now, there is a very logical explanation for this, but at the moment we don't yet have the tools to show why this property must be true. We will, however, return to this property in a future lesson and prove why all non-zero numbers raised to the power of 0 must equal 1. For the time being, just recognize that all of these expressions must evaluate to be 1. Also recognize that our original definition of exponent requires some modification. Originally, we said that the exponent tells us how many times to multiply the base by itself. However, as we have seen, this definition doesn't really help us evaluate expressions where the exponent is equal to 0. The original definition will also be hard to apply when the exponent is negative. After all, what does it mean to multiply 10 by itself -2 times? Or what does it mean to multiply 8 by itself 2/3 times? So just know that our definition of exponent will be modified later in this module. Okay, now let's continue with more exponential properties. The next property concerns expressions where the exponent is equal to 1. Now, as you might guess, 8 to the power of 1 equals 8, and in general, we can say that any number x raised to the power of 1 will equal x. We can also write this property like this. So all of these expressions will evaluate as follows. Next, we will examine situations where there is no exponent. In this particular example, 6 can be rewritten as 6 to the power of 1. In fact, if a number does not have an exponent, then the exponent can be assumed to be 1. In other words, x is always equal to x to the power of 1. So all of these numbers can be rewritten using exponential notation as follows. The next property concerns even and odd exponents. Now, to set this up, what is the value of negative 1 to the power of 82? Well, if you said 1, you're right. One way to evaluate this is to multiply negative 1 by itself 82 times. Or we can evaluate this by making a few observations. First, notice that negative 1 to the power of 1 equals negative 1. Negative 1 to the power of 2 equals 1. Negative 1 to the power of 3 equals negative 1. Negative 1 to the power of 4 equals 1, and so on. Now notice that when the exponent is odd, the expression evaluates to be negative 1. And when the exponent is even, the expression evaluates to be positive 1. To generalize these results, we can say that a negative number raised to an even power will yield a positive number, and a negative number raised to an odd power will yield a negative number. Now, if we build on these results, we can say that odd exponents preserve the sign of the base. For example, negative 2 to the power of 5 equals negative 32, and 10 to the power of 3 equals 1000. In both examples here, the exponents are odd numbers. In the first example, the base is negative, and the result is also negative. In the second example, the base is positive, and the result is also positive. Now, if the exponent is an even number, the expression will always evaluate to be positive regardless of the sign of the base. Now, please note that there's one exception here. If the base is 0, then the expression will evaluate to be 0. Otherwise, if the base is a non-zero number, then the expression will always evaluate to be positive regardless of the sign of the base. So in these two examples, notice that the exponents are both even, and notice that regardless of whether the base is negative or positive, the result is always positive. Okay, let's see how these properties affect the following equation. Since the exponent of 3 here is odd, we know that the sign of the base is preserved. Since 8 is positive, we know that x must be positive. So this equation has one solution, x equals 2. Now let's examine this equation. Here the exponent of 2 is even. If the exponent is even, the expression will always evaluate to be positive regardless of the sign of the base. So in this equation there are two possible solutions. X can equal 2 or x can equal negative 2. Now before we conclude this lesson, it should be mentioned that it is quite useful to memorize certain powers in order to save time on test day. The powers that are typically tested include the powers of 2 up to 2 to the power of 7, the powers of 3 up to 3 to the power of 4, the powers of 4 up to 4 cubed, the powers of 5 up to 5 to the power of 4, and all powers of 10. Now please note that the powers of 10 are easy to memorize, since the exponent always tells us how many zeros follow the 1. So for example, 10 to the power of 5 is equal to 1 followed by 5 zeros. Okay, let's summarize. In this lesson, we learned exponential terminology and how to evaluate powers, and we learned some important properties of exponents.